So yeah, needle in a haystack paradox, building robust data detection with scarce logs. It's a mouthful, isn't it? So this is a very data science heavy topic, right? So I'm not assuming that everybody who is sitting in front of me in a security conference is fully aware of data science and its concept. So this will be a very beginner friendly topic, right? So start with who I am. My name is Athul Raju. I work for Oracle Cloud Infrastructure. I lead their threat detections team. I do similar research. So if you are interested, feel free to reach out. Alright, so what exactly is the problem I'm trying to say here? So this is a typical data science problem. It's called class imbalance, right? Sometimes it's referred as extreme class imbalance. It changes. Now what exactly it is, when you're trying to build a model, a detection model or any model, with a bare minimum, like a very limited set of true positive logs, then something like this can happen, right? That means the true positive logs or the actual attack logs is only when it's only a fraction of the total volume, this can happen, right? Now, some of you might be thinking, right, why are you trying to introduce a problem to me and then provide a solution to that? It's a very interesting question if you think about it like that, right? See, when you think about threat detections, right, the first thing that comes to your mind is SIEM, right? The query-based detections in SIEM, right? They can solve a lot of problems, right? They can solve a lot of problems. But as the attack vector gets sophisticated, right, we have reached a point where we have to introduce data science, AI, ML, and deep learning into the detection building capabilities. Now, this is a problem that is caused by that, right? Now, like I said, let me explain to you, like all of you, how a typical model is built. Like, I'm taking an example of something called a classifier models, right? So how a classifier model is generally built, then I'll introduce like how this problem can happen there, and I'll propose two solutions, right? Alright, so let's talk about building a classifier. What are classifiers? Now, classifiers are models that can give you Boolean outputs. 0, 1. True, false. Buffer overflow, not a buffer overflow. Instance principal stealing, not an instance principal stealing. So it can give you a Boolean output. Now, what are the essential factors you need to build a model like that? Obviously, you need an algorithm, right? Model algorithm, it goes by a different name. Let's not talk about algorithm for a second, right? Because algorithms you don't need to create an algorithm yourself, right? If it's ML, it's there. You can use the Python libraries. Scikit-learn has a lot of ML models, algorithms. Now, if it's deep learning, you can use Keras, PyTorch, etc., right? So algorithms are there. What you need to do is train the algorithms, right? Train the models. Now, how are you going to train the model? It's pretty much like a baby, right? Like a child, right? You need to teach it something for it to find it in the future. So think about it like that, right? For you to train the model, you need data sets, logs, right? So you're basically teaching the model how a buffer overflow would look like, right? Through logs, right? You are actually feeding it with the real buffer overflow log or any security use case log and teaching it, okay, this is how a buffer overflow would look like, right? Then what happens is you finish your training, then test the model with unseen data, right? What are unseen data? Data which were not part of your training set. That's how you measure the performance of a model, right? You're training the model and then following it with testing with an unseen data. Okay. That's whole pipeline, basic a high-level overview of a pipeline. Let's take an example, right? Now, this is my use case. We want to build a model, right? All of you want to build a model. Now, this is our objective. We need to build a model to recognize the presence of a lion in an image, right? Very simple, right? You feed the model with an image and the model should tell you, again, Boolean, like true or false. The model should tell you whether that image contains a lion or not. Pretty straightforward, right? Nothing complex about it. Now, how do you build such a model? Obviously, step one, choose an algorithm, right? Since it's an image, you'll have to use something, a neural network, right? Now, what else you need? Data set. You need to train the algorithm, right? Train the model. So for that, what you need? Obviously, you need to train the model with real pictures of lion, right? You will have to train the model with real pictures of lion from a diverse set of environment, right? You cannot train the model with the same image of like 100 lions, like copy of same image, and expect it to work for unseen data. It does not work like that. You need to have a diverse set of data. Diverse set of data means lion from different angles, right? Lion under different lighting. Lion from different ecosystem, right? Lion in a zoo. Lion in a forest. Lion in a house. Now, once you feed this information to the model, it will obviously understand the features of a lion, right? Obviously, whiskers, hair. It will understand the features of the lion. And later, if you test it with an unseen data, it will be in a better situation to predict the presence of a lion from an image, right? Now, model can make mistakes, right? Model can make mistakes. We make mistakes. Remember this guy from last year? No. Even for a split second, we thought it's a lion, right? I mean, from that picture, from this picture, that this can happen, right? Model can make mistakes. Now, so we have successfully built a model, right? Now let's build one more model, similar approach, nothing is going to change. Now instead of lion, we are going to find the presence of a different animal here, right? Whole different animal. We're going to build a model to find the presence of a unicorn. Have you seen unicorns? Now we haven't seen unicorns, right? What's the problem here? Do we have enough data sets for images of a unicorn like we do have for the lion? No, right? We don't have. That's the problem. Now, without enough data set, how are you going to train the model? How are you going to train the model and teach it like these are the features of a unicorn? How are you going to do that? Well, this exactly is class imbalance. Right? We don't have the data set to actually train the models. Now, think about it for a second. Is it an algorithm problem? This is not an algorithm problem because the same algorithm successfully classified lion. Is it a data set? Is it actually a skill set problem? The skill set gap within an engineer? No. The same engineer built the lion is unable to build something for a unicorn. So this is precisely a data set problem, right? One of the most common problem in cybersecurity these days. Now, can we fake the data? Can we dress up a donkey like a unicorn and get some pictures and train the model? No, it does not work like that, right? Obviously, we can synthetically create some data. You can use AI, to create some data, but that might not be enough, right? Like I said, the data has to be diverse, right? How much you can create with synthetic data? So there are limitations. So let's go back to security for a second now. I'm going to say, let's compare the unicorn use case with insider threat. Now, we have a similar problem here. Insider threat, obviously, very common these days. We don't really have enough insider threat logs within a company, right? Obviously, we should maybe have a handful of logs. We can synthetically create some of the logs. But how is that different from unicorn? Now, that is not different. They are basically the same. From a data science point of view, these are similar problems. They're not different. They're similar problems. Now, so like I said, that is class imbalance. It's pretty much a data set problem. Now, why am I talking about a data science problem in a cybersecurity conference, right? And why is this not a problem in field like aviation or medical sciences? Have you thought about that for a second? The reason is, in the field of aviation and medical sciences, there are so much going on, right? There are awesome models out there. There are models in medical sciences that can successfully identify cancerous tumors from scan reports. Why is it not a problem for medical sciences? And why is this a problem for cybersecurity? Data set sharing. right? In the field of medical sciences, aviation, etc., the data set is pretty much shared, right? If an air crash happens, that information, including the telemetry, is shared with pretty much everyone in that domain. Even the air crash investigation report is released publicly. Anybody can read. Is that the case for cybersecurity? It is, right? To some extent, it is. But for sensitive and complex use cases like, say, insider threat, that's not the case, right? Nobody is going to share you the telemetry of our insider from their company. Because obviously it is sensitive, right? Which means we will have to deal with this problem, right? Now, that means SOC will have direct implications. Threat detection team, hunting team, IR, intelligence team, they need to understand about this. That's why this is a unique cybersecurity problem. Now, let's talk about the solution with a demo, right? So I have a demo. Now before I dive into the demo, I need to just talk about a couple of things. One is about the dataset I'm using for the demo. Now specifically, I'm talking about insider threat. So I have used the Carnegie Mellon University insider threat dataset. It's an open source dataset. You can download it from their official website. Specifically, I'm using the R5.2 email logs. It's email logs, right? So what you can expect, all the fields associated with an email, right? So that is sender, receiver, BCC, CC, subject, attachment, all those information, timestamps, etc. It's a basic email logs. Now, before I move on to the demo, I just want to share one more thing, right? How is a good detection measured today? It's query-based detection. I'm not talking about model-based detection. A good detection today is measured basically based upon the number of true positives it creates, right? If it generates far more true positives than false positives and blind positives, we generally say it's a good detection, right? Now, it's not that easy for a model, right? For measuring the performance of a model, we have 4 different parameters: accuracy, precision, recall, and F1 score. Now I'm going to make a bold statement here. I'm going to say, in the case of class imbalance data, accuracy is not a great measure. I'll prove to you why. Now, precision and recall. There is formula out there. I mean, taking a look at the formula, if you're good enough, it's awesome, right? But forget about the formula for a second. The recall is a detection engineering parameter. What is recall? It's basically how well your detection is performing to find true positives. That's a simple. Think about that. It's like that. Precision is a SOC feature, SOC metric, right? More the precision, less the noise. Less the precision, more the noise. So think about it like that. That's a SOC feature, SOC metric. This is a detection engineering metric. Now, F1 score is very, very important. It basically is a combination of precision and recall. Now, moving on, let's talk about the baseline model. So what I have done here is, I've made you 3 experiments. One is testing the Carnegie Mellon University logs, which is heavily class imbalanced. I'll show you the logs. And first what I'm trying to do is I'm running it against a baseline model without any fixes. After that, I'll apply 2 techniques. Are these the only 2 techniques out there for class imbalance? No. There are so many other techniques, right? But these are probably easiest technique to follow. Sometimes the easiest techniques are most of the time the effective techniques, right? In this case, they are. But the effectiveness of a technique changes from dataset to dataset, right? Alright. Let's go to the notebook. Alright, so one thing I want to share here is like, in data science, data pre-processing is so important. I'm not going to talk about data pre-processing for now. It's basically like I'm starting from step 100. Right? There are 99 different steps, which is all commented out here, which need to be done. What am I doing there? I'm basically transforming my log sources, right? In this case, the email logs from Carnegie Mellon. I'm doing a lot of things there. I'm doing normalization. I'm doing transforming. I am getting rid of outliers. I am understanding the features of the columns or features. The whole process is sometimes called as EDA, exploratory data analysis. Obviously, I build features myself. There is one reference to feature engineering, which means I'm finding new features or columns, right, from existing columns, right? It can be a combination of multiple columns from the logs. Long story short, there are 99 different steps I'm not going to share with any of you because of the time constraint. I'm starting from step 100. Okay, this is our log source. Now, one other thing I want to share here is, since Carnegie Mellon log is like, it is a simulated log. It's not a real log. Okay. So they have actually done the labeling, right? What is labeling? They basically have gone through line by line, log by log, and labeled it 0 or 1. 0 means not an insider activity. 1 means an insider activity. So in this case, I have around like 400k non-insider activity and like basically less than 2000 insider activity. You see the difference, right? The true positives are basically less than 0.4% of the total volume. Now, this is a class imbalance step. Alright. Now, one other thing I want to tell you here is like I said, remember I talked about unseen data, right? Unseen data where you test the model with. So what I'm doing is from the entire data, I'm telling 0.7%, that is 70% will be used for training, and 0.3 will be used for testing purposes. So I'll be training with the 0.7%, like 70% of the logs, and rest 0.3 will be used for the testing purposes. Alright, the first technique, like I said, the baseline technique without applying anything, it's going to be, I'm using logistic regression. Logistic regression is a basic classifier, a linear classifier. What it does is basically, this Boolean result. It will say whether insider or not. Same thing. No different. Now I'm running the logistic regression, and then this is my output. Accuracy 99.98%. Precision 0 equals 0. F1 scores 0. It has a very high accuracy, right? This is why I said, like, sometimes accuracy can be a misleading information. Why does it have a very high accuracy and pretty much everything else 0? Remember the formula of accuracy from the previous slide? The formula of accuracy is true positive plus true negative by total. So basically what's happening here is, model is doing a great job in finding zeros and a horrible job in finding ones. How did I know? Because recall is 0. So basically, model is doing every bit of his skill to find zeros, but it is not even finding a single insider activity. That's why I said accuracy is a very irrelevant metric when it comes to a class imbalance data. Alright, now let's apply the Alright, let's apply the first fix, right? So, alright. So, now, remember this guy from X-Men, I don't know if you remember, his mutation is, he can multiply himself, right? He's from one of the X-Men movie, I forgot. So, he can multiply himself. Remember the first fix, which is a data level fix, it's called smooth. What it does is, it multiplies the minority. Right? In our case, the minority is ones, the insiders, right? It multiplies the minority. From the unicorn analogy, it's not creating the copy of the same unicorn. More or less like creating multiple copies of, say, unicorn cousins, right? Similar copies, but not identical, right? How is it doing? It's using something called a kth nearest neighbor algorithm. But yeah, that's what it is doing, right? Now, How do you apply smooth? So this is how you do it. So you're telling the algorithm that I need the minority to be 50% as much as the majority, in this case 0. So it's a very aggressive number. I normally don't start with 50%, but for the sake of demo, I'm giving an aggressive number. So what does that mean is, my insider activity will be 50% as much as the non-insider activity. Now I run the model. It's similar, like I'm running again logistic regression with smooth applied. These are my numbers. Accuracy is around the same, right? 99.51. There is a slight increase in recall and precision. Obviously, if precision and recall increase, F1 score will increase. But is that enough? No, that's not enough. I cannot productionize this model, right? But there is a slight increase. Now, let's talk about the last technique here. The last technique is very easy to remember. It's called cost-sensitive learning. It is like penalizing the model. What you're doing here is, you're penalizing the model if it wrongly classifies an insider activity. Basically, you're applying a weight, right? Every time model make mistake in finding once, you're applying a weight. What does that do? There is something called, the whole process will repeat. Sometimes called backward propagation. It's like looping the whole thing, right? Now, once the model makes makes a prediction, it will go back and then based upon the mistake it had made in the first iteration, it will try to fix the parameters to make the second adjustment. Now, what model does is, what cost-sensitive learning does is, every time it makes a mistake, it is applying a weight, right, to the model, so that model next time, in the next iteration, will try to classify the minorities correctly. It's a algorithm level fix. Smooth was a data level fix. This is an algorithm level fix. So how do I apply that? Pretty straightforward. I have defined a weight. Now then what I'm telling here is, if it wrongly classifies 0, I don't care, right? Give a weight of 1. If it wrongly classify 1, which is insider activity, apply a weight, okay? So that model can recorrect it in the next iteration. Now after applying that, these are my number. Accuracy dropped, right? Accuracy dropped to 61. Recall is 0.48. Right, almost 50%. What does that mean? Well, it means the model successfully managed to detect 50% of the insider activities. Well, that is a big jump, right? Check the other two methods. That's a massive jump when compared to other two algorithms. But can I productionize this model? No, why? Because see the precision. It's very low number. If I productionize this model, SOC will be flooded. Right? SOC will be flooded. It will be a real needle in a haystack. So the SOC will be flooded, but obviously it will find some insider activity. But nobody cares. If it's a flood and 1 or 2 insider popped up here and there, that might go missing, right? So I cannot productionize this model also. Alright, so alright, so going back, right, what have we learned here? Baseline model only has very high accuracy. It doesn't mean anything. It has a very poor, almost zero, right? It's almost zero, it's zero. Zero precision recall F1 score. Now, the second, for the data level fix, slightly increase the recall and precision, but again, not a production worthy model. Now, the last method, the cost-sensitive learning, obviously it increased the recall to almost 50%, which means it successfully found 50% of the insider activity, but with a very low precision, right? Can I make the model even better? Yes, I can, right? There are so many other methods, right? I can make the model even more better. Like I can make it maybe like 70%. I don't know. I haven't tried this with the algorithm, but there are so many methods out there by which you can make the model perfect. There are actually hybrid methods specifically for cybersecurity. These are not given away. These are part of my research. There are so many methods you can apply here to increase the model, but none of them will be perfect. None of them will be as good as, say, a model from the medical sciences which I mentioned. None of them will be that perfect. The answer to all this problem is not finding a model with the very high performance. It will always be identifying the model with the best trade-off. That's all, right? You cannot build a perfect model when there is class imbalance. But obviously, if you can identify the right trade-off, you can live with it. That's all. That's pretty much it. Thank you. Questions?
I bet the same thing. Yes, same conclusions. But I tried a different approach. I tried different methods for generating synthetic data.
Yeah.
But I got the same conclusions. There's always a trade-off.
Yeah, there is. But there are so many other methods you can fix it. Like I said, cybersecurity. What you can possibly do is something called like context enrichment, right? Try to increase the true positives even before it reaches the model, right? That's the 99 steps I mentioned earlier. You can do a lot there, right? If you are good at, EDA, like really good at EDA, not the data science EDA, security-wise EDA. So that's a whole different thing, right? Every time you think about EDA, you go to think about Kaggle, right? The Kaggle.com. That's not how you do EDA for security. If you can learn the EDA really well, and if you have a good support from SOC, where they label the data really well, you can increase the number of repositories.
Sorry, we need to cut it. There's one last presentation that's going to happen up in track 1. So if you want to view that, I'd say move upstairs because they're going to start in about 30 seconds. Thank you.
Thanks.
Thank you for the presentation.